So in this lesson, we're going to start off our study of sequences with just the basic definition. So a sequence is a function whose domain is the set of positive integers. And if you remember, the positive integers would be things like 1, 2, 3, and so on, all the way up to infinity. And the definition includes the fact that a sequence is a function. So the notation is going to be pretty similar to what we saw earlier in the course, but we will use different representations. So instead of having, for example, y equals f of x, we're going to have now a sub n equals f of n. And with our domain, our independent variable needing to be positive integers, you can see that when we plug a 1 in, we get a sub 1. When we plug a 2 in, we get a sub 2. 3 would give us a sub 3, all the way up until we get to the nth term of the sequence. So the set brackets on either side generally are used to denote a sequence. But the first term would be a sub 1, the second term would be a sub 2, and so on. If there are a finite number of terms, we call it a finite sequence. And if there are an infinite number of terms, we would say that it is an infinite sequence. So in the first example we'll look at, this is an nth term formula. An nth term formula is a function, is a formula that generates the terms of a sequence. So in this one, we're going to write the first 4 out. But before we jump into that, I do want to refresh everybody's memory that the factorial notation is in this example. So a factorial, again, just kind of as a side note, if I gave you 5 factorial, that's the same thing as 5 times 4 times 3 times 2 times 1, which would give us the 120. So also kind of as a note, 0 factorial by definition is 1, and then 1 factorial is also 1. So anyway, we'll get back to our example here in blue. The first thing we're going to do is find the first term. So we need a sub 1. So similar to what you would have done in function notation, every place you see an n, you're going to put a 1. So negative 2 times raised to the 2 times 1 minus 1 over 1 minus 1 factorial. And when you clean all of that up, remember in your denominator, 1 minus 1 is 0, 0 factorial is 1. So when you clean all that up, you get a negative 2 for the first term. The second term, we would go ahead and we'd plug in a 2 every place we see an n. And again, in that denominator, be careful, you'll have a 1 factorial. A 1 factorial is 1. So when you clean all this up, looks like we get a negative 8 for the second term. The third term would be very similar. Every place you see an n, put a 3. In that denominator, 2 factorial is going to be 2 times 1. So in that denominator, you get a 2. When you clean it all up, you'll get a negative 16. And then finally, a sub 4 means every place you see an n, put a 4. And in that denominator, our 3 factorial would be 3 times 2 times 1, so a 6. And we get a negative 64 over 3 when that last term is simplified. So there are the first 4 terms. The original right here, this nth term formula, was the formula that generates these terms in the order you see them. All right, so now we'll look at a recursion formula. And you need to remember, a recursion formula is an nth term formula. Okay, so a recursion formula is an nth term formula, but it's a special one. It's an nth term formula that generates the terms of a sequence using the previous term. So using the previous term, that's the key to a recursion formula. So For example, if we had a sequence a sub 1, a sub 2, a sub 3, a sub 4, then we would find a sub 3 by using a sub 2. So in general terms, if a sub n is our current term, then the previous term would be a sub n minus 1. So the notation there is very important. There will be a sub n minus 1s in our final answer here, because to build up the current term we need to use that previous term. So let's take a look at the example that's given to us here. We give a sub n equals 1 minus 1 over a sub n minus 1. And they always have to tell us where to start. For example, we can't find a sub 2 without being told a sub 1. The good news is it's very similar to the last problem we worked. If we have a sub 1, a sub 2 means go inside the sequence, the nth term formula, and every place you see an n, put a 1. Put a 2. We're doing the second term, so every place you see an n, put a 2. But when you simplify that, you can see that's going to give you a sub 1 in the denominator. So 1 minus our a sub 1 was 1/2, so our a sub 1 was 2, so I plugged the 2 in there. 1 minus 1/2 gives us 1/2. So we'll go ahead and do a sub 3. Every place we see an n, we're going to put a 3. And when you clean that up just a little bit, you can see how we're now dependent upon using a sub 2, which was the previous term. And when you clean that up, you get a negative 1. A sub 4, every place you see an n, put a 4. And using that previous term, looks like our a sub 4 is going to be a 2. So we've found the first 4 terms, but it also asks for the 8th. Now, we don't have to find a sub 7 to get a sub 8. We don't have to find a sub 6 to get a sub 7. We're in a unique situation here where all of a sudden now we've got a repeat. Well, remember, the next term would be based upon the previous term, so I know that my a sub 5 is going to be dependent upon a sub 4. So if you can follow the pattern now, using 2 into our original formula, you can see that the next entry, the next term, would be the 1/2. A sub 6 would be the negative 1. A sub 7 would be the 2. And finally, the a sub 8 would be the 1/2. So it would just keep following that same pattern over and over again, because you're using the previous term, which we've already calculated in an earlier step.